Welcome back to quantitative reasoning. Last time we learned how to make box plots, a visual way to summarize quantitative data. In this tutorial we learn how to make histograms, which display more detailed information about the distribution than box plots. We're going to use the data in the pre-installed iris data frame again. Last time we wrote a script iris.r in which we made this box plot that shows how summary statistics, such as the median or the range, differ between species. Suppose we now want to see the distribution of the sepal widths for the species versicolor in more detail. Let's first save versicolor's sepal widths in a variable so that later on we won't have to type so much. Let's call the variable sw_ver as an abbreviation for sepal width of versicolor. We assign to it the subset of the values in the column sepal.width, for which the value in the species column equals versicolor. From tutorial 8, we know how to accomplish this task. First, we take the vector iris$sepal.width, then we use the logical vector iris$species == in quotes versicolor for subsetting. Let's take a brief look at the content of sw_ver by typing the variable name in the console followed by the return key. There's one number for each measurement made by Edgar Anderson. The command length (sw_ver) confirms that there are 50 measurements for iris versicolor, which matches the number we found with the table function in tutorial 13. Our goal is to make a histogram of the values in sw_ver. The command for it is hist (sw_ver). Note that when we use the hist function, the argument in the parentheses must be a numeric vector with one number for each observation. From the histogram in the bottom right pane, we get the impression that the data are unimodal and a little bit skewed to the left. We can change the appearance of the histogram by passing more arguments to the hist function. Many of the arguments have the same names that we encountered when we worked with the boxplot function. For example, the argument col equals in quotes light green changed the histogram's color to light green. We can change the title with main equals and in quotes sepal width of iris versicolor. When we click run, we can see the title at the top of the plot. The argument for changing the x-axis label is xlab. Let's call it width in parentheses centimeters. Let's insert some line breaks to make this command more readable. The order of the arguments col, main and xlab doesn't matter. For example, we may move main in front of col. The plot is still the same. The only important thing is to keep the data to be plotted, here sw_ver, at the first position in the argument list. The appearance of a histogram is greatly influenced by the position of the breaks between the bins. In our case, R decided to put the breaks at 2.0, 2.2, 2.4, and so on. Sometimes it's worth playing with the break positions ourselves. We change the breaks by inserting the breaks argument into the hist function. For example, if we want to place the breaks at 2.0, 2.1, 2.2, 2.3, etc. up to 3.4, we write breaks equals c and in parentheses 2.0, 2.1, etc. up to 3.4. The c function is exactly the same that we've used since tutorial 2 to create vectors. When we copy and paste only the c command to the console, it returns 2.0, 2.1, and so on. Sequences with equally spaced numbers, such as this one, are quite common in R code. For this reason, R has a shortcut function to avoid tedious typing, the Scq function. Scq takes 3 arguments, the start and end values of the sequence and the step width. So the equivalent of the long C command above is Scq and in parentheses 2.0, 3.4, 0.1. Let's copy this command into the breaks argument above. Make sure that you close as many parentheses as you open. In this case, there are 2 consecutive closing parentheses at the end. Now run the new hist command so that we can see how the new breaks change the histogram. Does it look better? We can switch between this and the previous figure by clicking the arrows in the top left of the Plots tab. When the bins are larger, the distribution looks smoother, so we can see the overall unimodal shape more clearly, but the smaller bins reveal more details. There's no simple rule how many bins we should use in a histogram. In fact, it's good practice to try different bin sizes because they can reveal different features of the data. As long as we stay away from extreme choices for the bin sizes, we can set the bin sizes such that they best support the message we wish to convey. Let's summarize what we've learned. In R, we make histograms with the hist function. There are multiple arguments to the hist function that change the histogram's appearance. For example, col changes the color, main the title, and xlab the x-axis label. The breaks argument sets the position of the breaks between bins. A useful function when adjusting histogram breaks is the Scq function. It creates a regularly spaced sequence between two numbers. Next time we learn how we can save the histogram plot as a file. See you soon.